Okay, looks like I'm live now. Let me see. Let me figure out things first, how I can manage everything. I think I figured out a lot of details just now for live streaming, but still not thorough with everything. I don't know where I'll be seeing the chats for the same thing. If someone joins. Okay. I'm just checking at the analytics page. If someone has already joined in. Just text me on phone if you know me personally, or drop a message somewhere. Where? Okay. Yeah, I have a post here. That's increasing shorts and it's that. Okay, content I have. Videos, shorts, live. Analytics view in live control room. Okay, there is a live control room. Okay, there's the chat there. Okay, now I have it. Now I have everything up and ready to go. Okay, welcome to my first ever live stream. So it's weird talking to myself. I know there is nobody in the live stream, but this is for the reference for later as well. I'm just let me see. Let me find my words. I'm not prepared. Okay, so this won't be the single outstanding live stream. I'll keep continuing my coding journey here. My main intent is to learn. With that, if the YouTube channel grows or the community grows, it's good. Otherwise, also I'll be on the side of benefit. I mean, I'll be benefited a lot if I'm disciplined to learn. That's why I won't give importance to a lot of fascinating things unless it comes easy, like editing or setting up the studio or things like that. But I'll try to focus on the content and what I'll be learning. For now, I'm kind of focusing on data structures and algorithms. I wouldn't say the interview prep as a whole, because different people will have different necessities for interview prep. I mean, the junior engineers would have different skill sets that they need to work on, and the senior software engineers would have different ones. And coding is not just for software engineers. There might be not just for software developers. There might be DevOps engineers, data analysts, data engineers. A lot of people might have coding questions, and also someone who is learning and hasn't even applied or prepping for the interviews also might be curious about how to write simple codes. They are also welcome to join in and observe. And I would say, like, if someone was doing a coding live stream, it would have been boring for me. So I'll come from that point of view. How to make it less boring? Please ask relevant questions. I'll try to treat it as, going forward, personalized classes. I mean, I won't go out of the way to learn about some graphic design or some low-level stuff in order to stream here for someone's benefit. But if it is something in my domain of expertise or related to that, which I'm also curious about, I'll try to learn and present here, or we can have some collaboration. I can learn from someone and I can just broadcast our stream here. That's the intent. And my plan is I'll just go ahead with algorithms and data structures for now, and probably system design to some extent. After that, I am planning to learn few concepts of machine learning. I have a couple of courses which are open and available to everyone. So maybe doing it as a group or completing that course as a group gives the accountability, and also it would give me an opportunity to understand more, I guess. So I will do that. So yeah, that's the near future plan, and by then at least I would have figured out a lot of things here in lives, like how to live stream, how to make others experience better, and things like that. Today my intent is to focus on graph algorithms and prepping about graph algorithm questions and the concepts, starting from some concepts and theory about how graphs works, how the traversals works, DFS, BFS, Bellman-Ford. Yeah, I've forgotten what lies ahead. So main thing is like to figure out the shortest paths, to figure out all the paths, figure out dependency indexes or dependency graphs, and I think Bellman-Ford is for negative weight, I guess, if I'm not wrong. So yeah, let's see. I have few resources which I have mentioned in the description as well. LeetCode is the best source for any coding problems, and Gail McDowell's cracking the coding interview. That's like the Bible for any interview preparation. I would say, I mean, nowadays I haven't heard a lot of chatter about it, but I would say still it's the best resource because it covers the basics very nicely, very neatly. Like just by going through cracking the coding interview is kind of like sufficient full preparation. That's what I had done during my masters, because that covers a good sample size of all types of problems, which gives us the ability to attempt other types of problems which are not there in that as well. So that's why I like to start with that. And then there is a list called Blind 75, which is available on LeetCode as well. I think the same problems. So solving that problem, I mean that list is a comprehensive list. I kind of like that as well. And GeeksforGeeks, it's one of the older resource which I used to refer during my masters, and it's available publicly, so it covers the basics well as well. So we can go through that one by one and see whichever is more fun or whichever is more relevant, and try to grasp the concepts there and learn. So I'll be using these modes. This is my full cam mode, and if anybody in case joins here and has any questions, feel free to ping me. I'll try to address it at the instance. I'll try to have some focus time started as well, or focus timer, when basically I'll try to start the focus timer only when we are solving certain problems or things like that. So hey Kota. So yeah, there will be two modes. So I'll have this LeetCode stream. I'll have a focus timer here. So when I'm solving a problem, let's turn on the focus timer and try to attempt to solve the problem. If we cannot solve it, we can go back and look at the solution and try to understand it. And we can have a time boxed evaluation of theory as well. Theory, I mean to say, like I cannot try to solve the problems without understanding the basics of data structures or the algorithms as per se. I need to revise those concepts every time I come back. I I remember it. I remember what is graph, what is graph traversal, what maybe I might remember DFS, BFS, but I don't remember Dijkstra's, how to code it, or the details about it, or Bellman-Ford, or anything like that. So need to go through those things. So today I'll try to go over the graphs basics. So let me see. So these are certain modes that I'm thinking. So you can see here. You can see I've opened this one. This is the one I usually refer whenever I'm starting. You might not be able to see this one. So this is the algorithms graph search, DFS and BFS. This is like 11 minutes video, but it's too much information, too much good information. Whenever I want to start any data structure preparation, I start with this this playlist of published by HackerRank, and it's very informational. Okay. So once maybe I'm thinking how to structure this one in the live stream. Should I just turn on this video and we can watch it together and we can add comments, and if someone has questions they can add it in the chat as well. I can pause it and we can analyze it together, and then we can go over the concepts here. There are various different ones like covering BFS, TFS differences, and some problems or examples given, and the shortest path. Okay, I think this is kind of extensive list, I feel. Wow, these are a lot of things. I'm not sure if we will be covering all that. Okay, but all this seems familiar, not this one, but I have heard Prim's, this one, minimum spanning tree, Kruskall's minimum spanning tree, but yeah, not for a long, like not in a long time. I think I had heard it when I was doing my masters, like in this one, using in this book I had read all those algorithms, but don't recall anything. Let's see if we can go over that. Okay, let's play it then. Let me know, Rahul, if you have any trouble hearing it. Can you hear it?
Like breadth first search and depth first search. So to go back to the beginning, a graph is basically a collection of nodes where each node might point to other nodes, and these edges can be directed, so like one-way streets, or undirected, so kind of like two-way streets. Now, suppose you want to go walk through this graph, and specifically, suppose you want to do something like figure out, is there a path from one node to another? There are two common ways of doing this, and we'll talk about both of them. The first one is a little bit more simplistic, and it's called... Hi.
Okay, I'm not sure if the audio is...
Hi, I'm Gail Lock-McDowell, author of Cracking Coding Interview. Today we're going to talk about graphs and common operations like breadth first search and depth first search.
So to go back to the beginning, a graph is basically a collection of nodes where each node might point to other nodes, and these edges can be directed, so like one-way streets, or undirected, so kind of like two-way streets. Now, suppose you want to go walk through this graph, and specifically, suppose you want to do something like figure out, is there a path from one node to another? There are two common ways of doing this, and we'll talk about both of them. The first one is a little bit more simplistic, and it's called depth-first search. And it's a typically recursive algorithm. And the way it looks like is saying, okay, we have this initial node that I'm going to call S. Now, you basically are asking the question, hey, S, do you have a path to node T? And S says, I'm not sure. Let me go ask my children. And first S goes to node A and it says, hey, A, do you have a path to node T? If you do, then hey, I'm done. I can give you my answer. If you don't, then let me go ask B and then C and then D. And so the very first person we ask is A. So A gets asked, hey, A, do you have a path to T? I'm not sure. Let me go ask my children. And eventually we might get to a node who says, why, yes, of course I have a path. I am T. And so then we go and say, boop, 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 all the way back up, yes, there's a path. And that's the basis of depth-first search. It's called depth-first search because we go deep into some node before we even ask any of the children. Now the problem with this is that we might run really, really far away. So imagine, for example, that B actually has a path directly to node T, has an edge directly to node T. A might go to all of its children, all of its children, all of its children, before you even get to B, and T was right there. There could have been a really fast connection. So that's why we might often prefer to use breadth-first search instead. Breadth-first search says, hey, go level by level out. So first, we ask S, hey, do you have a path to T? And S will say, well, let me check if any of my nodes are T. No, there's no edge right there. So each of those get in line. And then we ask the second level out, and then the third level out, and the next level, and next level, next level. And so we go level by level, breadth, we go wider before we go deep. And that's why it's called breadth-first search. So I want to talk at a high level about the implementation of each before I dive into some of the details. So depth-first search is implemented with a recursive algorithm. It's probably the simpler algorithm to implement. The only little trick is that you have to make sure to use an isVisited flag so that you don't wind up in some sort of infinite loop where there is, a cycle and you keep asking each node if it has, you start running around in a circle. With breadth-first search, the main trick you need to remember is you want to use a queue. So when you look at S and you say, hey, do you have a path to T? You're going to go add all of its children to the queue. And rather than going recursively, you pull out the first element from the queue, check if it has a path, and check if it is this final element, and if not, go add all of its children to it. So you use a queue so that you go through things in the correct order. So that's at a high level how it works. Let's turn to the real details of the implementation now. I've gotten a bit of a head start on the implementation, but I'll show you just quickly what I've done. So first we have this node class here, and it's going to have some sort of ID that represents the node ID. And what I've done is give ourselves a mapping from node ID to the actual node. And this is mostly going to be used for things like get node and add edge. This way we can actually just go and get immediate access to the node with a particular ID. And then I've also given us this has path depth-first search method, and it's going to call out this recursive method. So if you remember with depth-first search, we need to have a way of flagging nodes to say, hey, I've already visited this, don't retry it. So one thing we could do is we could actually modify the node class to give ourselves an isVisited flag. But that requires then making sure we clear that flag later on. Another way of doing it is giving ourselves a hash set that lists all of the IDs that of the nodes that I've already visited. It's sort of a replacement for a flag. So I'm going to do it this way I don't have to modify and add a whole bunch of flags in and then make sure to clear them later on. So I get the source node, I get the destination node, and then I create this visited hash set, and then I go out and call this recursive method. So now's where the fun begins. So first, if I've already visited this node, if visited.contains this source ID, then return false, because there is no path then. Okay, otherwise, then what I want to do is, so now I want to go and make sure I update this, mark this node as visited. And then I want to say, okay, if I'm at my source, then return, if I'm at my destination rather, then return true, because yes, there's certainly a path then. Otherwise, go and check all my children, see if any of them have a path, because if there's a path from a child to me, then there's certainly a then there's certainly a path from me to my destination. So for each node to child in source.adjacent, if there's a path from child to destination, passing in again visited, then return true, and that'll bubble all the way up the stack. If I get down to the very end and I haven't found a path yet, then there is no path from me to my destination. Now let's turn to how breadth first search works. Okay, so breadth first search. So what I need with breadth first search is I need a linked list of sort of what I'll call the next up. So these are I'll call this next to visit. These are the nodes that I need to visit next. And just as before, I need this visited hash set that represents everything I've already visited. And then I want to say next to visit, first thing, because the first thing I need to visit is in fact my source. Then as long as there is nothing in this, so while visited, while next to visit dot is empty. So while it's not empty, keep going. All right, so first thing, I need to grab my very first node to visit. So node equals next to visit dot, I'll call this remove.
Okay, let me start from the beginning.
Hi, I'm Gail Locke McDowell, author of Cracking Coding.
Let me start from the beginning. I wasn't doing a good job. I was trying to adjust the sound somewhere. I'm not sure if it is clearly audible as well. Maybe I can try to set it later, since there are not many viewers. So I'll try to get back to the video again, and I'll stop and comment in between as she adds something.
Interview. Today we're going to talk about graphs and common operations like breadth first search and depth first search.
Okay.
So to go back to the beginning, a graph is basically a collection of nodes where each node might point to other nodes. And these edges can be directed, so like one-way streets, or undirected, so kind of like two-way streets. Now, suppose you want to go walk through this graph, and specifically, suppose you want to do something like figure out, is there a path from one node to another? There are two common ways of doing this, and we'll talk about both of them. The first one is a little bit more simplistic, and it's called depth first search. And it's a typically recursive algorithm. And the way it looks like is saying, okay, we have this initial node that I'm going to call S. Now, you basically are asking a question, hey S, do you have a path to node T? And S says, I'm not sure. Let me go ask my children. And first S goes to node A, and it says, hey A, do you have a path to node T? If you do, then hey, I'm done, I can give you my answer. If you don't, then let me go ask B, and then C, and then D. And so for the very first person we ask is A. So A gets asked, hey A, do you have a path to T? I'm not sure. Let me go ask my children. And eventually we might get to a node who says, why yes, of course I have a path. I am T. And so then we go and say, boop, 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 all the way back up, yes, there's a path. And that's the basics of depth first search. It's called...
That's the basic of any recursion algorithm. Basically, in each node, what we are doing is we are just checking if the neighbors have a path to destination. Like there is a source given and there is a destination given. The problem is to figure out if there is a path between source and destination. So now all I'm doing is I'm just checking with my neighbors. Like let's say in the real world, like if I'm checking like what's the path, it's just like whoever are my immediate neighbors, I'm checking with them saying that okay, do we have a path to reach to this destination? That's it. And then that neighbors also would do the same thing. They will check with their immediate neighbors and then pass it along. And then once they receive the information about like whether there is a path or not, then they will bubble it up or come back in the recursion, and the same information would go to the source node as well. So that's how the recursion is working in BASIC.
Depth first search because we go deep into some node before we even ask any of the children. Now the problem with this is that we might run really, really far away. So imagine, for example, that B actually has a path directly to node T, has an edge directly to node T. A might go to all of its children, all of its children, all of its children before you even get to B, and T was right there. There could have been a really fast connection. So that's why we might often prefer to use breadth first search instead. Breadth first search says, hey, go level by level out. So first, we ask S, hey, do you have a path to T? And S will say, well, let me check if any of my nodes are T. No, there's no edge right there. So each of those get in line. And then we ask the second level out, and then the third level out, and the next level, next level, next level. And so we go level by level, breadth, we go wider before we go deep. And that's why it's called breadth first search. So I want to talk at a high level about the implementation of each before I dive into some of the details. So depth first search is implemented with a recursive algorithm. It's probably the simpler algorithm to implement. The only little trick is that you have to make sure to use an is-visited flag so that you don't wind up in some sort of infinite loop where there is a cycle and you keep asking each node if it has, you start running around in a circle. With breadth first search, the main trick you need to remember is you want to use a queue. So when you look at S and you say, hey, do you have a path to T? You're going to go add all of its children to the queue. And rather than going recursively, you pull out the first element from the queue, check if it has a path, and check if it is this final element, and if not, go add all its children to it. So you use a queue so that you go through things in the correct order.
Okay, just reiterating the same thing what she very clearly explained. So the main difference between depth first search and breadth first search is using depth first search, even if your neighbor is the destination. Let's say, for example, the example she gave was from A to T. If we say A is the source and T is the destination, and if we happen to go to C first to check if its neighbor is the destination, then we will keep going in depth, like from C to its neighbor, and from there to its neighbor, and from there to its neighbor, and then we keep checking until we get to the leaf node. And the same way, like we will check all the possible paths here, like from here we will go here, all these ones, and then same thing until we encounter a visited node or we encounter a leaf node, we keep checking. So now A is the visited node. But with breadth first search, we go level by level. So from A, we will check all of its neighbor if it is the destination. And then once we are done with A, we will move to C. And then we'll move to C means we'll go to its neighbors one by one. To C, we will ask it to check its neighbors, direct neighbors, just the direct neighbors. We'll go to this one, we will go to this. Okay, those are the only two neighbors. And with D, we'll go to only this node and check if that is the destination. With E, we will go to this node and we will check if that's the destination. And with S, we will come and see if this is the destination. And we'll add S, C, D, E to visited list. And then once we come to, and then we would have to iterate through these ones. So we would use a linked list or a queue for this purpose. Like those are, like in the linked list, what she has added is to be visited nodes. Basically, those are the nodes to be visited. Initially from A, she added all of its direct neighbors as to be visited, and once we came to C with these nodes, she added these nodes to be visited. And then, like when we come to the next level, these are the ones in the queue. We will check its neighbor. It doesn't have, okay, it has this is the only neighbor it has, but I think we have to check. And then with this one, we have only this neighbor and this neighbor. Those two are not the destination. We will add it to the queue. And then with B, we come here and we see that, okay, the T is the destination. And then we found that, okay, there is a path between A and T. We will return true at that point of time. So if we exhaust the entire graph without finding it by going layer by layer, then we will say that okay, the path doesn't exist. That's the best. That's the difference between breadth first search and depth first search. As I understand it, the worst case scenario is the same for both of them, but breadth first search gives an organic way or an organized way to go from layer by layer without missing the nearby vertex or the nearby nodes only.
So that's at a high level how it works. Let's turn to the real details of the implementation now. I've gotten a bit of a head start on the implementation, but I'll show you just quickly what I've done. So first we have this node class here, and it's going to have some sort of ID that represents the node ID. And what I've done is give ourselves a mapping of from node ID to the actual node. And this is mostly going to be used for things like get node and add edge. This way we can actually just go and get immediate access to the node particular ID. And then I've also given us this has path depth first search method, and it's going to call after this recursive method. So if you remember with depth first search, we need to have a way of flagging nodes to say, hey, I've already visited this, don't retry it. So one thing we could do is we could actually modify the node class to give ourselves an is visited flag, but that requires then making sure we clear that flag later on. Another way of doing it is giving ourselves a hash set that lists all of the IDs that of the nodes that I've already visited. It's sort of a replacement for a flag. So I'm going to do it this way I don't have to modify and add a whole bunch of flags in and then make sure to clear them later on.
Okay, these two methods are nothing but, like, if someone's not familiar to Java, basically hasPath is the method DFS. What she has done is she has created a node class. So but in general, the question was asked with just a source and destination as an integer variable. So she has a wrapper class around it to which is kind of passing the node as a parameter. And to get the node as a parameter, they have a hash map or something. Where was it? They had a map where they had maintained a reference from the integer value to the actual node value. So yeah, this get node method will return that actual node, and then that is returned, and that is being passed on to st here to this method.
So I get the source node, I get the destination node, and then I get create this visited hash set, and then I go out and call this recursive method. So now where the fun begins. So first, if I've already visited this node, if visited.contains the source ID, then return false, because there is no path then. Okay, otherwise, then what I want to do is, so now I want to go and make sure I update this, mark this node as visited. And then I want to say, okay, if I'm at my source, then return, if I'm at my destination rather, then return true, because yes, there's certainly a path then. Otherwise, go and check all my children and see if any of them have a path, because if there's a path from a child to me, then there's certainly a there's certainly a path from me to my destination. So for each node child in source.adjacent, if there's a path from child to destination, passing in again visited, then return true, and that'll bubble all the way up the stack. If I get down to the very end and I haven't found a path yet, then there is no path for me to my destination. Now let's turn to how breadth.
Okay, to explain it line by line. So this is a recursive method where it is like checking if that source is already visited or not. If the source is already visited, just return false. If it is not, then add it to visited now, because we are visiting it now. And then if source is equal to destination, that means yeah, we found the path like we were looking for, like we already reached the destination, and we are asking you whether you have a destination from we have path for destination from here. So we will return true from there. Otherwise, what we will do is we will ask all of its neighbor to check if you have a path. That's what they are doing here. So they are like looping all the adjacent node, looping across all the adjacent nodes, and passing that as a source node, and keeping the same destination node and visited intact, so that we don't keep revisiting the same thing. And then if there is a path, then returning true. If there is no path after looping through all the adjacent nodes, then returning false.
First search works.
Okay, so breadth first search. So what I need with breadth first search is I need a linked list of sort of what I'll call the like next up. So these are the, I'll call this next to visit. These are the nodes that I need to visit next. And just as before, I need this visited hash set that represents everything I've already visited. And then I want to say next to visit, first thing, because the first thing I need to visit is in fact my source. Then as long as there is nothing in this, so while visited, or sorry, while next to visit dot is empty. So while it's not empty, keep going. All right, so first thing, so I need to grab my very first node to visit. So node equals next to visit dot, I'll call this remove. So remove the very first node in that list. If this is my destination, then there's certainly a path. Now I also want to do my visited checking. So if visited dot contains of node ID, then actually just continue. Let's go to the next value. Otherwise, visited.add of node.id, so mark it as visited. And then go and actually add my children. So for each node child in node.adjacent, go and add each of those to my next to visit. So next to visit.add child. All right, and that's all there is to breadth first search.
Okay, just to reiterate the same thing, I cannot explain better than her, or I don't explain better than her. But if someone's not paying attention here, so BFS, so the difference between the approaches for BFS and DFS is BFS, we will go level by level, and for DFS, which is depth first search, for depth first search, we will go into the entire depth and we will come back to the same level, and then next we will go to the next depth from the next leaf or the next neighbor. So that's the intention. So in order to achieve that, for DFS, we need to use a stack data structure. In stack data structure, it is naturally last in first out. So last in first out means basically whatever the neighbor we visit, and then like we would have added all the neighbors, but on top of that, once we take out the first neighbor, then we will add its neighbors, and then we'll take out the first neighbor. From there also we will add its neighbors. And then it keeps piling up at the top, and we will be getting the last added node to keep assessing or keep traversing. So that's why it keeps going to the depth rather than going level by level. And the same thing is simulated by recursion. Recursion uses the language's call stack rather than us defining the stack data structure explicitly. Here in BFS, or the breadth first search, we are using queue, or linked list acts as a queue, where we are like adding like here we are simulating like first in first out. Whichever entry we are adding first, we are removing that, and then we are iterating through that. So if I was writing the code here, I would have added the queue here. I mean queue class here. I don't know why she created an instance of linked list class here. So I would have created a linked list class, but would be of the type queue. Then we would be able to access queues methods like queue.offer, queue.poll, or queue.offer, those ones. Other than that, here the same thing she is doing. Next to visit is the source, and then we are coming and we are checking if until the queue is empty, we will keep we'll keep doing the same thing, and we are taking up the first element in the queue, and then if the element is equal to the destination, then return true. Otherwise, we are adding it to already visited. We are checking that, okay, if the current node ID is already existing in the visited, then we will go out of that loop. Otherwise we will add the current node into visited hash set, and then we are kind of iterating through all. If it is not visited yet, If it was not visited yet, then we are adding all of its adjacent neighbors into the next visit queue, so that okay, the first one among these will be picked up, and then we will keep going to the next level and check the same thing. Even there in the next level, if we find the next visit, or the node in the next visit is equal to destination, then we will return true. Otherwise, we will add it. We'll check if it is visited, then we will just walk out of the loop. We won't add its neighbors. If it is not visited, then we will add it as visited, and then we'll add its neighbors to the next visit list, and it keeps going on.
And then, of course, if I get down to the very end and I haven't had a path yet, return false. So let's walk through this code again and make sure that this makes sense. So HasPathDFS takes in the source and destination IDs, and then I get those nodes, and then I create this hash set. That should be a hash set, not a hash map. And then goes and actually does this recursive method. So the recursive method has this visited thing, so we use the visited hash set instead of marking the actual nodes with a flag. So the visited checks if it contains the source ID. If it does contain that, if I've already visited this, return false, because there's no path then. Otherwise, go and add this visited, mark this node as visited, check my source and my destination, show them already there, return true. Otherwise, go and search all of my children. And then if I haven't found a path, go return false. So with BFS, we are taking in a source and a destination. So here I've used nodes. All sources actually be symmetric, and use IDs again. And so I'll make that public and this private now. Okay, so I take in source and destination IDs, and then I go and call this recursive method. So my recursive method, this other just help method. So this takes in the source and destination. I create this list of the next nodes I have to visit, and this visited hash set, which should be hash again. And this marks all the nodes that I've already visited. So I say, okay, next one to visit is my source. Then as long as there's something left to visit, pull out the next node to visit, check if I'm where I should be, if so, return true. Otherwise, check and update my visited, who I visited, and then go and queue up my children at the very end of the queue to be visited next. And this will ensure that my children are not visited immediately, but are visited once sort of everything's scheduled to already been visited. So it'll ensure it'll visit level by level by level. And then if I get down to the very end and I haven't found a destination after all of this, then just return false. So that's how breadth first search operates. In many cases, when we want to find if there's actually a path, breadth first search is often the better approach, because otherwise we could wind up searching really, really far away when it's actually a very short connection. And it's certainly better when we want to find the shortest path. So now that you've seen breadth first and depth first search, why don't you try these out on a new problem? Good luck.
Awesome. That was good. Let me see if there are any other graph-based.
Did you know that Amazon?
Okay. Data structures, cycles in the linked list. I think there might be some playlists, I would say. That would be a better source. Yeah, it's data structures here. And we don't have to play it yet.
Hey, so
Let's see, data structures. Where did the graphs go already? Is it somewhere here? Okay. Then that should be it from HackerRank, I guess. Okay. Solve the shortest reach using BFS. Okay, and that's something. Connected cells using DFS. You can look into these two later. We can go in order, like she explained DFS and BFS. We can just quickly go through that, but let's take a quick break for some time, and for some, let's say 7 minutes, and then we can come back to the stream. Okay, I'm back now. So let's see. I think I should be better than the previous session in managing the streaming and what to expect from here. Yeah, we just saw a uh, video of uh, basically this video. I'm back now. Okay, basically the video from HackerRank from uh, talking Gail McDowell talking about the graph algorithms. I mean, basically DFS and BFS and the graph search algorithms. This is pretty informative and very simple to implement. Stop research. So, okay, this account I have ads, so can't help that. Let's go back to graph algorithms in GeeksforGeeks. This has a lot of information. If I see here, we need to filter out and make sure that we are covering the important ones to start with. If we have more time, we can go back to uh, come back here and solve more problems. But at least I can cover the breadth for search. That's pretty much covered in the last one. DFS is covered, and okay, difference is covered. We can revisit it here. We can go to each of these topics and see. Okay, this representations. I think I just wanted to see the basics of it. Okay, somebody's pinging me. Okay, representations of the graph. So let's see here in this case. Let's time box it. So what all things we need to cover first? So there are 4 viewers. I don't know. Feel free to add a comment if you have just joined. This is new for me. Let's close this one. Okay, now we are back. A lot of technical difficulties, maybe a lot of rendering going on for the ads here. That could be the reason. Okay, we need to go through the representations, breadth for search, depth for search, and then we can directly skip to maybe something like a Dijkstra's shortest path. That is something we need to look into, and then Bellman Ford. Um, let's make a list of things that we need to um, go through. Okay, I have this one pretty good template for interview preparation. Not template, I mean the one I'm managing for myself. It makes it easy for me. Okay, I didn't plan to open it in this session, so no, continue with Google. Use another account. Maybe I should have hit that screen. Okay. Here I have the problems and the things that I need to cover. So I was going through graphs today. So let's see. Here, graph traversals, and then DFS, DFS, the extras, then Bellman Ford. I think that should be good, and then we should select few problems and try to work on those. So let's go to the graph representation. Okay, here I can see, okay, graph is a non-linear, okay, consisting of vertices and edges. This is obvious. The vertices are sometimes referred to as nodes and edges are referred to as okay, edges connect to any two nodes in the graph. More formally, a graph is composed of, okay. So the two ways of representation is adjacency matrix and adjacency list. So what is adjacency matrix? In adjacency matrix, way of representing a graph as a matrix of Boolean zeros and ones. If there is an edge from vertex I to j, mark adjacency matrix of I of j as 1, otherwise it's 0. So let's say here they have a good example. 0, 1, 2 as 3 nodes or vertex they have given for an undirected graph. So what is undirected means, like if there is an edge from 0 to 1, then we can assume that there is an edge from 1 to 0 as well. It's not like directed from one vertex to another. Like it exists in both the directions. So in this case, we have like, and there is no connection or the edges from the same node to the same node. So 0 to 0 there is nothing, and then 0 to 1 there is an edge, so we have marked it as 1, and then 1 to 0 there is an edge, so we have marked it as 1, and then 0 to 2 there is an edge, and 1 to 2 there is an edge here, and in the same way 2 to 1 there is an edge, and 2 to 1, 2 to 0 there is an edge, so 2 to 1 there is an 1, so they have marked that as 1 and the others should be 0. So this is uh, adjacency matrix representation. Okay, I'm just trying to respond to one of my friend who was in the stream. Okay, so the adjacency matrix representation, and the same thing is given in the code here. I'm referring to the Java only, maybe it took it from default or something. Okay, so in the main method they have add edge. Okay, they have just defined a matrix to represent this one. Vertex means number of vertex is 4, and okay, and then they have added a few edges here, and then asked to display the matrix. So matrix is displayed this way, adjacency matrix representation. And then representation of the directed graph as adjacency matrix. Okay, here in this case, I think I already spoke about this one. So there is, in this one, it is a directed graph. So if there is an edge from 1 to 0, that doesn't mean there is an edge from 0 to 1 as well. So here in this case, we can see from 1 to 0, we are marking it as 1. But 0 to 1, we have nothing, because it's directed from 1 to 0 only. So that's the directed graph. And at the same time, from 1 to 2 there is an edge, so we are marking it as 1 to 2 there is an edge and marking it as 1, and 2 to 0 there is an edge. So those are only 3 edges we are representing here. And here comes the adjacency list representation. So in adjacency list, what they are doing, an array of lists is used to store edges between two vertices. An array of lists, okay, the size of the array is equal to the number of vertices. Got it. So this is also a list of lists, but not like um, lists of lists. Even the matrix is kind of a list of list. So what's the difference? So in this list of list, we are just in this list of list we are just keeping the ones which has value, and here um, in this list of list we are not just uh, keeping the edges, but we keep the ones where we don't have edges as well. So yeah, so this is not a right representation to be used if there is a sparse matrix like sparse graph or something. What I mean to say is if there are hundreds of nodes, but if they don't have a lot of edges interconnecting between them, if let's say if each of those edges connects to its neighbor, or maximum two or three nodes, two or three edges from each node, then this representation will consist mostly of zero, right? Like from zero to all the nodes, it will be zero from but one or two nodes. So just maintaining that zero value, it's a waste of the space. Uh, and here in the adjacency list, so we will just keep the list of whatever the edges we have, nothing else. List of list. So now we have a list here. At the zeroth index, we are maintaining a list of edges or list of vertex to which we have edges. So at the zeroth index, we have edge to 1 and edge to 2. So we are maintaining 1 and 2 here. And then from the first index, you mean the first vertex, we have edge to 0 and edge to 2. So we have those two. So from 2, the same thing. And here we can see uh, we have what is number of vertices 4, but uh, we are defining the list of array list of 4, but it's a dynamic. We are defining it as dynamic memory or dynamic length. So as we add more edges, uh, the length will be determined. So yeah, no, I'm sorry. I think array list of v means it might be a fixed size one. So and then array list of integers. So the external or the outer list length is determined, but it is a list of lists. So the inner length is still dynamic. So we are going uh, through this adjacency list, or we are going through all the vertices, and then for each adjacency list, we are adding a new array list of dynamic length here. Okay, and then we are trying to add edge to each of those lists. So what they are trying to do here, add edge of adjacency list, and add edges one by one. So 0 and 1. Okay. Okay, now it is like this is the adjacency list. So they are passing the adjacency list and passing the values of uh, wherever the edges are supposed to be there. So yeah, and the representation would become like this. In in zeroth from the zeroth one, we have the edge to 1 and we have edge to 2. So from zeroth we have edge to 1 and edge to 2. From first node we have edge to only 2. So from first node we have edge to only 2. Oh, got it. But we have from zeroth node we have already defined that there is an edge to 1, right? So that means it is in like it is not a directed graph. So if we have edge from 0 to 1, that means we have an edge from 1 to 0 as well. So we have an edge from 1 to 0 also. So 0 and 2. And from 2, we have an edge to 3. And here we have defined from 1, we have an edge to 2. From 0 also, we have an edge to 2. So that means 2 has an edge from 0 and 1 and 3, all 3. From 3, we have defined just 3 has an edge from 2. So that means 3 has an edge from 2, 2 has an edge from 3. So that's it. So that's the representation. See, there are very less memory locations or the values that has to be stored with this representation, and it's easier to manage as well. Much more intuitive. Representation of directed graph as adjacency list here. Okay, directed graph. So here, like, I got confused, right? Like how this 0 came here, because from 1 there is only one edge that came because of this one. From 0 only we have defined that there is one edge. So that means it's reverse also, it's true. But in directed graph, that's not true. If we have edge from 0 to 1, that doesn't mean that we have an edge from 1 to 0. Okay, here let's see. This is a directed graph, and 1 to 0 we have a edge, 1 to 2 we have a edge, and 2 to 1 we have one edge. From 0 there are no outgoing edges, so from 0 there's nothing. It's an empty list now. From 1 we have an edge to 0, and we have an edge to 2, so that is there. And from 2 we have an edge to 0, so that is there. Okay, so that's about the representations. I think we can end it now. Let me know if someone has any questions, or if someone is there. Just raise your hand or give me a hint. Oh man, it's hard. I didn't think it would be so difficult to live stream, but it's good. I think for me it's hard to sit and study these days. It's good to focus this way. I think I'm doing much better because even if nobody's watching, I'm assuming that okay, people are watching and I'm trying to do my best here. Okay, I see there are two people, sorry, three people, but I don't know who it is. Maybe I can see it. I don't know how to see it. Um, yeah, at some point of time, one of uh, you were mentioning there is an issue with streaming, or the screen was frozen. Is it all right as of now? Okay, I don't know who are these three concurrent viewers now. Okay, let's refocus now. Representation is over. Next thing is we have DFS, BFS as part of the Geeks for Geeks here. I don't know if we have to go through that again. Let's go through that. It will be like a revision, quick revision. Let's time box these things. Otherwise, we will end up killing a lot of time. So let's, okay. Okay, Dijkstra's algorithm here. How to find shortest paths from source to all vertices using Dijkstra's algorithm. Okay, got it. So the same thing is there in the LeetCode. There are some good depth first search algorithms, like everything is covered comprehensively here for depth first search algorithm. And then some relevant problems here, I guess. It asks us to solve. I had looked into these concepts a little bit. There is something about breadth for search I'm yet to study. But yeah, I think we are covering the same thing today. There is minimum spanning tree, Kruskal's algorithm. Nice. Okay, Prim's algorithm. I have forgotten all that long ago. And single source shortest path algorithm, that is Dijkstra's, and Kahn's algorithm for topological sorting. Oh, I know this one. Core schedule 2. Okay, this is like to resolve the dependency graphs, I guess. So yeah, we can come to this one. So for now, let's quickly cover uh, this BFS and DFS, and we can try to solve few problems. How much time should we dedicate for this one? Anybody? Oh, concurrent viewers. 25 views. Wow, nice. What does it mean, 25 views? What, there 25 distinct people viewing this? Let me see. I'm just checking few things here. Okay, all good. Man, it's interesting to start a YouTube channel and study here. I don't know, it adds a dimension. Okay, I've of my friend written here. Okay, regular schedule can be easier to join here. I think I'll try to have a regular schedule. I am with, I think the whole intention of having this live stream is to uh, keep myself a proper routine of learning, like not just limited to algorithm and data structure. I think I'll continue learning things after this one as well. I'm having fun. I'm tired of talking, but it's kind of good. I might improve my communication this way. I think if I go to interview, the interviewer has to work hard to shut me up. I guess I'm talking so much. It's a practice, like a muscle memory. Keep talking. Initially, I was blank when I started the stream. I couldn't utter a word. It's because I was studying as I usually study. I don't talk to myself when I'm studying alone. So, man, okay, taking too much breaks. But I hope I'm not troubling anybody. Drop in a message if I'm wasting someone's time. Then I'll just try to speed it up, or I'll reduce my break time. Okay. Oh man, I'm just checking my LinkedIn message. Last one. sorry, I had to reply to this one. And done. Okay, anybody watching? Nobody. There is some viewer still though. I don't know. I don't know how to see the current viewers. Are there anybody? No? Total number of times the stream was viewed while it was live. Okay. Chat rate, the chat rate of the stream at the most recently available time. The number of viewers connected to the stream at the most recently available time. Okay. Total amount of time people spent watching the stream divided by the total number of views. Okay. Stream health, stream settings, everything looks correct. And stream health is in excellent condition. Okay, got it. I think everything is all good. We can go back to preparing. Okay, this time I'll make use of the timer. Yeah, so where is it? Okay, got it. So, does it move? No, doesn't move with me. So, how much time should I need to cover this? DFS, BFS. Can I change the time? Short break, long break. Okay, session rounds. This is nice. Cover together, and then next one could be what should it be? The extras, and then okay, and each of those. Okay, it would have been good. It would have been nice if we could assign timer for those. That would have been awesome. Stay focused for, let's say, 15 minutes now, and then let's wrap up DFS and BFS. Okay. Depth first search was all the adjacent vertices one by one. Adjacent vertex Okay, in DFS, we traverse all the adjacent vertex one by one. When we traverse an adjacent vertex, we completely finish the traversal of all the vertices reachable through that adjacent vertex. Okay, we'll go one by one. Like let's say um, in DFS, how can I explain it? So within our community, let's say if I have to figure out if there is someone with the name uh, um, Mark, let's see. So what I'll do is in, let's say this is depth first search, then I'll just, and assuming my neighbors are my, there is a neighbor on the left side of the house and the neighbor on the right side, and there is there could be a neighbor behind behind our house. So I'll start with the left side neighbor and then see, I'll ask if you know Mark, or if you are Mark. I'll just ask if you are Mark, or if you have a neighbor by name Mark, or if you have a patch Mark or whatever. I'll ask him, and then I won't go and ask the right neighbor, but I'll wait for him to gather me the information. Like until he says for sure there's no Mark, I won't go to the right neighbor or the neighbor behind. So now he will go, he will see, he will go ask his left neighbor if he is Mark or if he knows a Mark. And then if he is Mark, or if he is not Mark and if he doesn't know Mark, then he will go and ask his neighbor. Let's say if his neighbor is Mark, then he will say, yes, I'm Mark. Then he will tell the same thing to his neighbor. He'll tell the same thing to his neighbor, and then name information will bubble up or come to me. So, and then I'll say, okay, there is a Mark in our community. Let's say if they kept asking on their left side and there's no Mark on the left side of our community, and there's a Mark on the right side of our community, then what will happen is, and let's say I'm in the middle, like there's no connection from any of those nodes to the right side of the houses that I have. So then what will happen is they will all check, exhaust all the houses, and then they will come back to me and say that, okay, there's no Mark on that side of the community. And then what I'll do, I'll either pick the right side of my house or the house uh, back side, and then ask if you are Mark, or if you know someone with the name Mark. Okay, then the same process repeats. He keeps asking his neighbors, and then I'll wait until he comes back, and then if he says yes, I'll return yes. If he doesn't, then I'll ask the neighbor behind our house. So that is depth first search or depth first traversal. Okay, there can be multiple DFS travels of a graph according to the order in which we pick the adjacent vertices. Here we pick vertices as per the insertion order. Source vertices. Okay, here 1202. This is the input, means input is a graph, and output is 1, 2. Okay, here you can see start at 1 and then marked as visited, and then output 1. Move to 2 because 2 is one's neighbor, and then output is equal to 2, and then 0, which is 2's neighbor, mark as visited, output 0, and then backtrack to 2. There's no neighbors for this one. There's one neighbor which is 1, but it is already visited, marked as visited, so won't go back to 1. It will recoil or retrace back to 2, and then 2 will check, move to 3. So 3 doesn't have any neighbors as well. It will just mark 3 as visited and output 3, and then backtrack to 2, and then 2 has another neighbor which is 4, mark as visited and output 4, and backtrack to 2, and then 2 will backtrack to its parent 1. That's it. That's the traversal here. Not that there can be more than one DFS traversals of a graph, for example, after 1, we may pick adjacent 0 instead of 2. Yeah, I mean, both neighbor doesn't have any weightage or there's no rules to select 2 over 0. So there could be a different order altogether. It is 1, 2, 0, 3, 4. In that case, it could have been 1, 0, 2, 3, 4. Or 1, 0, 2, 4, 3. Yeah. So here, let's see. 2, 3, 1. 2, 3, 1 is input. 2, 3, 1, 0. What is 2, 3, 1? That means here. Okay, that means this is the 0th index. In the 0th index, you have edges to 2, edges edge to 3, and edge to 1. And from the first index, which is this one, there is a there is an edge to only 0, and from the second index there is an edge to 0 and there is an edge to 4. From the third index there is an edge to only 0, and then from the fourth index there is an edge to only 2. So that's the graph adjacency list representation. Clear? And then now we are starting from 0 here, and then from 0 we have choose to mark 0 as visited and output edit output 0, and then I have traversed to 2 marked as visited and output 2, and 2's neighbor is 4 marked as visited and output 4, backtrack to 2, there's no more for 2, and then backtrack to 0. Okay, next one is move to 3 and then mark it as visited and then backtrack to 0, 1. Yeah, clear? Awesome. DFS from a given source of undirected graphs. Okay. The algorithm starts from a, okay, what is this GFG practice? Curious. Oh, there is something like GeeksforGeeks practice. Don't know. Nice. Okay, I haven't visited GeeksforGeeks since a long time, so. The algorithm starts from given source and explores all the reachable vertices from the given source, similar to pre-ordered tree traversal where we visit the root, then recur for its children. In a graph, there might be loops, so we use an extra visited array to make sure that we do not process a vertex again. Yeah. So in tree also we traverse like in order, post order traversal, but we never maintain a visited map or visited set there. Why we maintain it in graph? Because in tree we don't encounter um, like a cycle or um, like there is a proper hierarchy from parent we are going to its children, and then none of the children would be a parent of its children. But here in the graphs it's like a relationship of neighbors, so all of them would be in the same level. Now a single node can be connected to multiple nodes at the same level, so there is a risk of traversing around the same nodes again and again. So that's why we maintain the list of our set of visited nodes. Let us understand the working of depth first search with the help of the instruction for the source as 0. Okay, let's see here, and this is not Java. Let's select Java. Okay, there is somebody else and wants to see some other language, let me know. DFS recursion or DFS recursive. Okay, recursive function of DFS traversal visited. They have visited of S as true. Okay, there's a list of adjacent static void. Okay, there is a static void DFS here, and there is a starting main method, main DFS function. Here you can see DFS. Sorry, this is the main method. Vertices, number of vertices is 5, and then we have adjacency list, and then adjacency list we have created list of lists, so we have added a new array list for each of those indexes, and then integer of edges, define the edges of the graph 1, 2, 1, 0. Okay, and then populating the adjacent list with the edges. Yeah, That is awesome. F0, okay, edge of 0 to edge of 1. So add edge, what it is doing, it is adding adjacency dot get dot add of t, adjacency dot get of t to s. Because it's undirected graph, it's adding edge to both the vertex, like both the nodes. From s it is adding t as a neighbor, and then from t it is adding s as a neighbor as well. So and then yeah, in setting the source as 1, so that's where we are starting, and then we are doing DFS traversal, DFS from source. So 1 2 0 3 4. Basically it should cover, or it should traverse to all the nodes and print it. That's the goal here. DFS traversal, complete traversal of disconnected undirected graph. So here let's see, disconnected undirected graph. Okay, um, undirected, okay, but disconnected graph, how can you traverse? Visit, okay, the above implementation takes a source as an input and prints only those vertex that are reachable from the source, and would not print all the vertices in case of a disconnected graph. Yeah, that's true. Uh, Let us now talk about the algorithms that prints all the vertices without any source and graph may be disconnected. Okay, so, so it doesn't require any source and graph could be disconnected as well. Idea is simple. Instead of calling DFS for a single vertex, we call the above implemented DFS for all the non-visited vertices one by one. Okay, non-visited vertices one by one. Yes, simple. Instead of calling DFS for a single vertex, we call the above implemented DFS for all the non-visited. Hmm. Makes sense. So we will maintain a visited list and we will call DFS on all the vertex. Ah, that makes sense. It's a good idea. Yeah. So what they're gonna do is, like, even though the graph is disconnected, so what we will do is we'll start with something random. We'll start with the zeroth vertex only, let's say, and then let's say 0, 5, and 3 are in one group, 1, 10, and 11 are in another group, and then 13 and 14 is another group. So, sorry, it is usually continuous numbers there. So if we have an exhaustive list of all the nodes, so we will iterate through all those nodes. We'll start from 0, and from 0 we will traverse. So 0, 5, um, 0, 5 something, whatever I told, 0, it will traverse all those nodes, and then 1, 11, so it will traverse those nodes. And then once we go to 13, 13 and 14, that is another node, another connected graph. So it will traverse that connection as well. Yeah. Okay, this is good. So here we see the main method adjacency list is created and then adjacency add. Okay, here you see 1 2 2 0. So these 0 1 2 are connected, and then 0 3. So these 0 1 2 3 are connected. 4 5 is not connected. So in this case we just added everything. 4 5 is a separate kind of disconnected graph, and 0 1 2 3 is another disconnected graph. So what they are doing is running DFS. In DFS, what we do is, here you see boolean visited, the same way we have maintained the visited. For int 0 is equal to 0, I less than v. So we are iterating through each vertices and then making sure that that vertices is not visited. If it's not visited, then we are calling the actual DFS method, DFS recursive method. In the DFS recursive method, it's doing the exact same thing that it was doing before. It is marking the visited as true for the current node that we visited, and then printing that current node, and then it's adding all of its neighbor, or going through all of its neighbors for int adjacent, like neighbors or the adjacency list. And then if one of those adjacent nodes are not visited, then it's going as calling the recursive nodes. Okay, that's it. Yeah, and the time complexity and auxiliary space. So time complexity is O of V plus E. So O of V plus E means it is basically it is directly proportional to total number of vertex and edges, um, and the same with the auxiliary space as well. So it is like basically we are uh, managing the list of list. So in the adjacency list format, basically the total number of rows depends on the total number of vertex, and the total number of or the maximum number of columns depends on the number of maximum number of edges that we get here. So that should be DFS. I think we can mark it as done, and we have our focus time burst already. Okay, let's take a break until this goes back to 0, and then we can come back. I'll try to set my screen better, I guess. So the DFS is done, right? Let's go to BFS now. This ad set might be troubling a lot of you. I don't have to broadcast that. Is it big enough? Can I make it bigger? Okay. I'm back. Hope all of you viewers can hear me. How many of you are there? 10,000 viewers at the same time. It's hard to answer all of your questions together. Oh, yeah, it's a good practice talking to me like that too. As a senior or staff level engineer, you need to keep talking. Like I think I lack at that. in wherever I'm working. Like I always feel hesitant to express my opinions. Uh, this way, I think that's a skill as well. Like now, I'm expressing my opinions, even though there is not a lot of people who are kind of uh, care about it as of now. At least they might care about it later when they watch my first live stream. Okay, let's start the timer now for 15 more minutes, and then let's get done with the what is that? Let's get done with breakfast search. Okay, timer started. Here you go. Breadth-first search is a fundamental graph traversal algorithm. It begins with a node, then okay, should be mostly similar to DFS, and we had understood what is breadth-first search, right? Like yeah, as contrary to what depth-first search was. Here, if I am looking for somebody with name Mark in our community, with using breadth first search, if he is somewhere near to me, like in my surrounding, 2 or 3 houses, the probability of finding him sooner is much more rather than by using depth first search. In depth first search, we will go to the extreme left and complete all the houses in on that side, and then we will go to the extreme right and complete all those houses, and then we will go in the backside of my community, backside of my house, check there. But if uh, Mark is in front of our house, so even if he is the next neighbor to me, I wouldn't have noticed him until I finish all these traversals. But as opposed to that, in breadth first search, what we do is I'll check with all my immediate neighbors. Okay, I checked with my left neighbor and then just pushed him to a queue. I checked with my right neighbor, if you are Mark, and then they said no, and then I push him to a queue. Check with the backside neighbor and the front neighbor, backside neighbor and push him to a queue, and front neighbor. If he is marked, then well and good, I'll just return true. If he is not marked, I'll push him to the queue as well. And then first, how the queue acts, like everybody knows, first in, first out. The first in was my left neighbor. So my left neighbor again goes through the breadth first search. So he will, and then I'll mark myself as visited. When my next neighbor comes, he will check his left, uh, and then if he's not marked, we just add him to the queue. He'll try to check his right, but right is already visited, so he wouldn't do anything. Check his backside, he'll check his front side, then the same cycle continues. At some point, if when the mark is found, or if someone with the name mark is there, then the response true bubbles up and up until the source, which is me, and then I'll return true. If not, we will just exhaust all the houses in the neighborhood, and then we will return false. There's nobody with that name. That's it. That's about breadth first search. Breadth first traversal just keeps going like waves, like a ripples or waves that are originating from a single point and then spreading across. Okay, uh, just let's just go through this one. Graph traversal. It begins with the node and traverses all its adjacent. Once all adjacents are visited, then their adjacent nodes are traversed. Different from DFS in a way that closest vertices are visited before others. We mainly traverse vertices level by level. So that's the right word, level by level. We traverse level by level. Popular graph algorithms like Dijkstra's, Kahn's, and Prim's algorithms are based on BFS. Okay, we can go through Dijkstra's. Okay, I think we have already that open. Next, now we will go through that next. The algorithm starts from a given source and explores all the reachable vertices from a given source. It is similar to breadth first traversal of a tree. Like tree, we begin with the given source. In tree, we begin with root and traverse vertices level by level using a queue data structure. The only catch here is that unlike trees, graphs may contain cycles. So we may come to the same node again. To avoid processing a node more than once, we use boolean visited array. Okay. Enqueue the given source vertex into a queue and mark it as visited. While the queue is not empty, dequeue a node from the queue and visit it. Okay. Okay, let's look into the code. Then it makes much more sense. Okay, in the main method, same procedure to create a graph. Vertices is equal to 5. That's why created a list of length 5 and then added all the adjacent nodes, means the vertices, and then then added all the edges, adjacent nodes to, initiated the adjacent list to an empty list, and then kept adding the edges 0 to 1. Since it's undirected, it will be like from both the directions, and then BFS starting from 0. So what he will do, queue, initiated a queue. Okay, this is how I would initiate it, by declaring it as a queue type and new linked list. Okay, and then boolean visited is equal to, okay, I would have used a hash set, but yeah, this works, and with minimal memory, I guess. So visited of s is equal to true, q dot add is equal to add of s. So added the source node to the queue and initialized it, and then iterate over the queue. While queue is not empty, poll the current queue, I mean current value in the pool. Poll the current value means what? Basically, pulled the first added value from the queue. Okay, and then printed it, and then just added all of its neighbor if it's not visited, like iterating through all of its neighbors, of all the neighbors of the current node, and then checking if that neighbor is already visited. If it's not visited, uh, then marking it as visited is equal to true, so that it is not added again as a duplicate from another neighbor, and then adding it to the queue. Okay, so we keep continuing it, and then we should get there. And yeah, it is mostly about traversal, so we are printing it, so we'll print all the nodes. So that's why we end up having this exhaustive traversal. And time complexity is O of b plus e, so depends on the number of vertices plus edges, and the auxiliary space that we use is O of b. So O of b is number of vertex only. So time complexity is understandable, O of b plus e. Because we will check with each nodes, each edges. Like we will go through all that and check, so that auxiliary space is directly proportional to O of b. So at most we are adding like whatever the existing vertex into the that additional queue. So that's the auxiliary space we are using. And why the auxiliary space was O of b plus e in DFS, if we remember? Maybe because we didn't mark it as visited before. We marked it as visited. I will like we didn't mark it as visited while adding to the stack only, but when we went to that implementation, okay, I'm confusing you more with that statement. I guess I think I can explain it when we get back to that. Okay, BFS of the whole graph, which may be disconnected. Got it. I think it might follow the same concept rather than uh, running BFS on from source to vertex. We might run BFS on each of the vertex if it is not marked as visited, by going through one by one. So what they are doing is, okay, the same way okay, it's not in Java. So the same way, basically creating a list and creating an adjacency list and adding all the edges, and then BFS of disconnected for this adjacency list. So BFS of it's disconnected, what it's doing is it's creating a visited map, or visited what you call this, um, array of visited, like where it can be indexed, and then if it is not visited, if this vertex is not visited, then only run BFS. So here, while running the BFS, we mark it as visited anyway if it is in the connected node of, like let's say we are going through 0th node, And then if it is connected to 0th node in the first shot itself, we mark it as visited. Let's say 0, 3, 4 are connected. 0, 3, 4, we mark it as connected. And then if 2 is not connected, let's say 0, 2, 5 are connected and 3, 4 are a separate disconnected ones. Then when we come to 0, 0 is marked as visited, 2 is marked as visited, 5 is marked as visited. So we will come to 1. So 1, if it is marked as visited, then we won't bother visiting. If 2 is marked as visited, we won't bother visiting again. If 4 is not visited, then we will again run BFS. Then in that BFS traversal, we mark 4 and 5 both as visited, as true. If and then we will check 5, 5 is also marked as visited, and then we are done with the traversal. That was good. Complexity and analysis of breadth for search and algorithm. Okay, BFS explores all the vertices and edges in the graph. In the worst case, it visits every vertex and edge once. Therefore, the complexity is OP plus E. Okay, that makes sense. BFS uses the queue to keep track of the vertices that need to be visited. In the worst case, the queue can contain all the vertices of the graph. Okay, that's as explained. Okay, applications of BFS. Shortest path finding can be used to find the shortest path between two nodes in an unweighted graph. By keeping track of the parent of each node during the traversal, the shortest path can be reconstructed also. Okay. Just if we need to find the shortest path, then we don't have to maintain anything like parent of each node. If we need to reconstruct it, then let's keep track of the parent of each node. Okay, so that we can traverse back. That's a good tip. Yeah. Cycle detection. BFS can be used to detect cycles in a graph. If a node is visited twice during the traversal, it indicates the presence of a cycle. Okay. If a node is visited twice during the traversal. Okay, like because of this one only, we might have to manage something called as visited. Otherwise, we will end up going to the same node again and again. Connected components. BFS can be used to identify the connected components in a graph. Each connected component is a set of nodes that can be reached from each other. Okay, got it. BFS can be used to perform topological sorting. Okay, each connected component is a set of nodes that can be reached from each other. Got it. Okay, we are just checking if two nodes are connected or not. Disjoint sets, I guess that's something called as topological sorting. BFS can be used to perform topological sorting on a directed acyclic graph. Topological sorting arranges the nodes in a linear order such that for any edge U appears before V in the order. So this is an application like in the real world we use very often. Even in our build systems, it might use BFS underneath in order to resolve the dependencies. Now let's say we will have so many packages mentioned as dependencies in our in the project, right? Like there will be hundreds of dependencies or thousands of dependencies, and the dependencies that we add, that will be that would have dependent on a lot more dependencies. So how do we handle the dependency resolution? So basically, now let's say package A depends on package B, package A depends on package B and C, and if package B depends on C again, then do we keep getting the same like multiple versions of C in order to finally package it? No, if it's the same version, we will get a single version of it. So in order to do that, they use this topological sorting, and then also uh, it should not be like a cyclic dependency there also. We can have a dependency resolution, and also like the same algorithm can be applied in a lot of different places. Level order traversal of binary trees. In binary trees, I think this is one of the main this thing. We know the in order traversal, pre order traversal, post order traversal. That's natural tree traversals. Level order traversals is basically going from top to down, level by level. So in each level, we'll go from left to right, not like we go through each nodes, but we care more about the levels. Network routing. BFS can be used to find the shortest path between the two nodes in a network, making it useful for routing data packets in a network protocol. Yeah, that's deep. But yeah, I think we can visualize it like in the nodes in a network. Between the two nodes in a network to send the routing packets, we use the network protocols use the BFS. Okay. Find the level of a given node in a undirected graph. Nice. There are a lot of useful problems here. Like I won't close it. Might have to come back to this one. And I think we finished it on time. What are the advantages? Okay. Shortest path on in the unweighted graph. Space complexity is O of V plus E. BFS has various applications, including finding the shortest path, detecting cycles in a graph topologically, sorting a directed acyclic graph, finding connected components in a graph, and solving puzzles like mazes and Sudoku. BFS is a graph routes and systematically explores the graph starts with a vertex and queues it into queue and marks it as visited. The queues, okay, got it. Everything's awesome. And our time's up. And I'm done with BFS. Next one is dice straws. Okay. Okay then. Dice straws. So should we give 15 minutes or 20 minutes for this one? Let's give it 20 minutes or 22, but after my lunch break or short break. Let me take a lunch break. After that we can go through this one. Dice straws. Okay, then I'll be ending the stream. If there is anybody in the stream, don't get disappointed. I'll be back. I'll start a new stream in some time. And I'll be here. I'll be studying for the whole month probably. I'll be creating stream like every day very frequently. And I'll have some agenda. I'll have proper agenda for each sessions and we'll go through that. And until now, for staying patient with me, thank you very much. And see you guys soon in the next